Okay, is it visible to everybody?
Yes, ma'am.
Okay. So in last lecture, we have started with design of continuous beam. This was the problem statement, and we discussed about how to calculate the load acting on each span of the beam, that is for span AB, BC, and CD. And we also considered the load coming from the slab. For this particular problem, all the three loads supported by the beam, all the three slabs supported by the beam are two-way slab. So how the load is getting transferred from two-way slab to the beam, that we had discussed. Okay, and then we solve the problem, or we analyze a problem for finding the moments. Okay, so the first step we completed, that is deciding the width of the beam, depth of the beam, then also the width of the flange, then effective span. Then we completed load calculation for each span separately, and then we came to the moment distribution method to find out the end moments. Okay, so these are the values. The same problem I completed further by completing the solution. Last time I had given you this as homework, and please now verify your answers with whatever I am showing right now. Are you getting the same answers, the end moments? Students, are you able to listen?
मॅम
Yes.
मॅम ह्या ज्या व्हॅल्यूज आहेत ना, ह्या ह्याच्यावरती स्लोप डिफ्लेक्शन मेथडने आहेत तसे सेम येत आहेत,
हाँ
बट डीएमनी आहेत ना थोडेसे चेंज होत आहेत. म्हणजे जी बी ची आहे ना,
हाँ
MBA ती
हाँ
29.18 होतीये, आणि
बर
BC ची निगेटिव्ह 29.18 होती,
ठीक
आणि
आहे.
जी CB ची आहे ती
हम्म,
42.52 होती, आणि CD ची आहे ती -42.64 होती.
ठीक आहे, नो प्रॉब्लेम, नो प्रॉब्लेम. थोडासा प्लस मायनस 1 किंवा 2 किलो न्यूटन मीटरचा फरक तुम्ही वेगवेगळ्या मेथड्स वापरून जेव्हा करता तेव्हा येतोच, अँड दॅट इज ऍक्सेप्टेबल. See the same analysis right now we have solved by considering moment distribution method. You can consider modified moment distribution method, three moment theorem, slope deflection method, Kani's method, any method which you found easy and suitable for you. Okay, any method you can use in the examination. You can do the analysis of the beam and you can find out the moments. Is it clear to everybody?
मॅम 2 किलो न्यूटनचा चालेल डिफरन्स? 2 किलो
चालेल
न्यूटन
चालेल
पर्यंत?
चालेल चालेल. ओके, तरी पण एकदा चेक करा तुमचे कॅल्क्युलेशन. 2 किलो न्यूटनचा डिफरन्स. अजून एक वाटल्यास नाही, पण तू स्लोप डिफ्लेक्शन वापरलेस ना?
नाही मॅम, एमडीएम काय होते, 28 च्या ऐवजी 29 येतं, आणि 44 च्या इथं 42 येतं.
अजून एक वाटल्यास हे सायकल पुढे कंप्लीट करा. नॉर्मली वेअर वी स्टॉप द डुईंग दिस सायकल, म्हणजे बॅलन्सिंग कॅरी ओव्हर हे जे स्टेप्स असतात, ह्या कुठे थांबवायच्या असतात? नॉर्मली वेन यू गेट द टू व्हॅल्यूज ऍट द बॅलन्सिंग लेवल अप्रॉक्सिमेटली सेम. आता इथं पण 0.30 आणि 0.25 एवढा फरक आहे, तसं 0.05 चा फरक आहे. सो दॅट इज ऍक्सेप्टेबल. हिअर ऑल्सो 0.45 अँड 0.41, सो दॅट इज ऍक्सेप्टेबल. अगदी 0.00 मध्ये सुद्धा व्हॅल्यू येतील जर मी हेच सायकल पुढे कंटिन्यू केलं तर. Okay, so the further next step, again I will carry over, and again when I will go to the balancing step, again I will get the accurate value. So accuracy increases with the increase in these number of steps: balancing, carryover, balancing, carryover. Okay, so if you stop earlier, suppose if I have stopped here at this level only, my value will be lesser. Are you getting my point?
येस मॅम.
हा. सो जितके तुम्ही हे सायकल्स वाढवाल तितकं तुमचं ॲक्युरेट रिझल्ट्स येतात. मी नॉर्मली स्टॉप at balancing stage when I get approximately equal value on both the sides. Okay, fine. So we'll consider these values now for further calculation. I hope everybody has drawn this bending moment diagram in your notebook. If not yet, just note down, just draw this diagram and these end moments. Okay, the next step is finding out the shear force values, or in other words, finding the SFD. Okay, and then we have to find out what are the span moments and what are the support moments, because without knowing the shear force distribution across a beam, we cannot find out what is the span moment and what is the support moment. Okay. Is it clear, everybody? Rather, the support moments we have already calculated here. MBA, MBC, whatever this moment we have calculated, it is nothing but our support moment. The moment at support B. Similarly, the moment at support C we have already calculated. But to find out the span moment, we need to calculate the shear forces first, SFD diagram or shear force diagram, and then based on that we can find out the span moments. Okay, so let us find out now the shear force values. For that we need to consider the span, each span separately. So this is our continuous beam which we have drawn in the last lecture. So the same beam we will consider again, but individual span, we will consider individual span, all the three spans separately, and then we'll calculate the reactions and hence the shear forces. Finding reaction means actually we are considering the we are calculating the maximum shear force values. Okay, so let us consider first the first span, that is span AB. So let us draw the diagram here for span AB. So I will just write down here calculation of, all of you write down calculation of shear force. Okay, so here I will draw first the diagram of a first span, that is AB, which is having a load of 23, am I right? 23 kilonewton per meter. लोड करेक्ट है का students?
Yes, ma'am.
Yes, ma'am.
Okay, so at A I will call, or I will give a name as RA, reaction at A, and at B I will note down it as RB1, because there is one more span BC, and when we consider that span separately we have to consider the reaction at B again. So the span is, I think, 3 meter, correct hai na? Span value?
Yes, ma'am. 3 meter.
Yes. Okay, so let us solve this beam further now, or the span of the beam. We know that summation Fy is equal to 0. We have to simply apply the conditions of equilibrium. So for summation Fy equal to 0 means Ra plus Rb, Ra plus Rb1 will be equal to the total load. What is the total load? It is simply 23 into 3. What is that total value? 23 into 3.
69.
69. Okay. So this is 69. Okay. Now to find out the reaction, let us consider the moment at A. Now you just don't forget the moment whatever we have obtained already through moment distribution method at the support B. So that moment also we have to note down here. So you just show the moment. What is the value of moment here? It is 28.74. Okay, so this is 28.74 kilonewton meter. So let us find out the first the reaction at B. So I will consider summation of moments at A. What is the summation of moments? Tell me. At A, first of all, the moment due to the external load. Okay, so it is 23 into 3 acting at a distance 3 by 2. So it is 23 into 3 square by 2. Now this moment is sorry,
Your screen is not visible.
screen is not visible.
Ma'am, it's blurred.
I will close it and I will again open it. Is it visible now?
Yes, ma'am.
Okay. Maybe I'm moving the screen, the page up and down now. Because of that, it may be taking time to set it as a clear screen. Okay. So let us find out the moment at A now. 23 into 3 into 3 by 2. That will be the moment due to the external load, and it is a clockwise movement. So I'm taking it as a negative. So this is minus. Then again here there is a clockwise movement of 28.74. So I will write down it as again minus 20. What is the value? Please tell me. 28 na?
28.74.
Yes. And then the moment due to reaction at B. So I will write down RB1 into the distance 3 meter. Okay. And this reaction is causing a anti-clockwise movement. So I will write down it as um, plus sign. So summation at A is 0. That equation we have written. So now simplify the equation and tell me what is RB1 you are getting.
44.08 kilonewton.
Just a moment. Yes, the value is 44.08 kilonewton. Okay. I hope everybody is getting the same value. Now let us make use of this equation RA plus RB1 equal to 69, and tell me, put the value of RB1 there and tell me the value of RA.
24.92 kilonewtons.
24.92 kilonewton. Okay. Similarly, now you consider the second span. The second span is this. Okay. BC for 17 kilonewton per meter with a span of 5 meter. So I will draw the diagram here again. So it is span BC. For the external loading of 17 kilonewton per meter with a span of 5 meter. Again, apply the same concept here. We have to find out the reaction at B. So I will write down here it as RB2 and this is as RC. RC1 again, because there is one more span beyond C, that is CD. So write down again the equation summation Fy equal to 0. So RB2 plus RC1, what is the value? 17 into 5.
85.
85? 85, correct. 85 kilonewton. Okay. Now similarly, you write down the equation for finding the moment. So I will consider summation at all the moments at B is equal to 0. So again, now I have to show the support or the end moments here acting at both these ends. So at B now, the moment value is 28.74, which will be in this direction, 28.74. And at C again, there is a moment. What is that value?
44.4.
Yes, 44.44. Okay. So consider all these values and prepare or write down the equation for summation of all the moments at B equal to 0 and tell me directly the values of RC1 and RB2. So this is whatever you have learned in your second year subject, MOS 1. So I'm not going to repeat the steps again because we have to finish problem today. Tell me the reaction RC1 and RB2.
Ma'am, RC1 is 45.64 kilonewton
45.64 kilonewton. Okay.
and RB2 is 39.36.
39.36. Okay. All right. Now, similarly, you have to consider the third span, that is for span CD. Again, RC2, I will call this, and this is an
परत स्क्रीन दिसत नाहीये. विंडोज दिसतंय फक्त.
एक minute. Okay. Meanwhile, all of you please carry on the further steps and find out the reaction at C2 and D. Or I mean to say RC2 and RD. Can you see now?
Yes, ma'am.
What is the load on span CD? Tell me quickly because I will not move now the screen up and down again and again. What is the load on span CD?
25 kilonewton meter.
And the span is, I think, 4 meter, right?
Yes, ma'am.
What is the moment at C? It is 44.44. There is no moment at D. So find out now RC2 and RD.
RD is 38.89.
Okay,
RC 61.11.
all right. Okay. So we have got all the reactions now. Let us draw the shear force diagram. So at A, what is the reaction?
24.92.
So I will go up 24.92. This is the upward reaction. Somebody from you have sent me on Monday itself the SFD diagram. So the diagram is little bit wrong. The reaction, the first reaction is going upward. So it should start above the datum line. Okay, not below the datum line. Who has sent me the picture or the SFD diagram?
येस मॅम ती कळलीच होत मला नंतर.
What's your name?
पार्थ मॅम.
Parth. Okay, okay. So the reaction is going upward. So the value of shear force should go up of above the datum line. Okay. So this is 24.92. The next, what is at C? What is the C value? RC1, tell me first. Sorry, RB1.
44.08.
So we have to go down with a 44.08 value. Okay, so this is 44.08. Then RB2, what is the value? So
39.36.
this is 39.36, correct.
RC1 45.64.
40?
5.64.
Okay, so it is 40, 45.61. So it will go up again. And
61.11.
this is 61.11. Please draw the proportionate diagram. I'm not able to draw it here properly. And then
RD
finally,
is 38.89.
yes, so it will go down again. 38.89 will go up again. So this is my shear force diagram, SFD. Okay, now to find out the span moment, we have to consider this is our first span AB. For this span, if I want to find out the span moment, I have to find out the point where my moment is maximum. And the easy way to locating that point is referring the shear force diagram. The point where your shear force is 0, at that point you will get the maximum bending moment, right? So we need that distance, and then only we can find out the span moments. So in this SFD diagram, we know this point where the shear force is 0, at exactly the same location we will get the maximum bending moment, which we want to calculate. So let us find out first this distance. Okay, so we already know this uh, uh, distance, or this we have to simply consider these two triangles as similar triangles and apply the concept of similarity of triangles. So this offset, or this distance is 24.92. This total distance is 3 meter, and this distance is 44.08. So let us call this as x, and the entire distance is 3 meters. So this will be 3 minus x, simple. And then apply the similar triangle concept here. I will show you for once, for one this value. So it is 24.92. I will simply write down here quickly, upon x is equal to 44.08 upon 3 minus x. Okay, so simplify the this relation and find out what is x you are getting. What is x?
1.08 meters.
1.08 meters. So this distance is 1.08. Okay, similarly in this span, we need to find out what is this distance. Let us consider this as y. Okay, and similarly in the third span, we'll require this distance. Let us call it as z. Find out quickly these y and z values and tell me fast. This is y and I want z also. In the same fashion as we calculated x by applying the concept of similar triangle, find out, considering the similar triangles in span BC, find out y, and considering similar triangles in span CD, find out z.
Ma'am, y is 2.32 meters
2.32 meters, okay,
and z is 2.45 meters.
2.45 meters. These values are only for this span, right? The value of 2 is from B, correct? Only
Yes, ma'am.
this much distance, huh? 2.32. I will just write down here 2.32 and tell me z again.
2.45.
2.45. Okay. Now let us find out the span moments quickly. Span moments. Now again consider the span AB. I will go back to the diagram here. Span AB. In this span, we have already located the point where there will be a zero shear force. That is, at that point, there will be the maximum bending moment. And I want a moment at that point. So that point is coming as 1.08 from A. So take moment of all the forces at point 1.08 from support A, somewhere here, say 1.08. Find out the moment at this particular section. You will get the maximum moment. So it is simply RA into this distance, and whatever the I will consider LHS. So RA into this distance and the whatever is the load acting in this particular span of 1.08, its moment about this section. So quickly tell me the equation. So I'm finding now the span moment. So I will write down this as MAB. Okay. So the reaction is, what is the value? RA
24.92.
24.92 into 1.08. Okay. So this is my clockwise movement and I have already shifted it to the right hand side. So I will write down this positive minus the load acting on the span is 23. Am I right? So
Yes,
23 into
ma'am.
1.08 square divided by divided by 2. So what is the moment?
13.5 kilonewton meter.
13.5 kilonewton meter. Similarly, now I have to find out MBC, the span moment for second span. Okay. Now for this span, I will go back to the diagram now, original diagram of your beam. Is it visible, this diagram? Diagram of entire beam ABCD. Okay, so I want to find out the span moment for span BC, and the location of the zero shear force is somewhere 2 point something. What is that value? Y value?
2.32.
2.32. Yes, 2.32 at within this span BC. So I have to consider, when I consider the section at 2.32 from B, I have to consider the entire left hand side of the continuous beam to find out the moment at this section. Okay, so simply consider this entire length, so 3 plus 2.42, and find out the moment at this particular section. Okay, so let us write down that equation so that you will find out the value easily. So the reaction RA is 24.92 into what is the value? 3 plus 2.32. So it is 5.32.
5.3.
5.32. Okay. Minus. Now the load acting on the span AB and load acting on span BC are different. The values are different. So you have to consider the moment due to these different values of the load separately. So let us consider first for span AB. It is 23 into 3, right? And it is acting at a distance 3
3/2.
plus, no, what is the distance? 3/2, correct. 3/2, no, I want the distance from the section where we want to.
5.32 minus 1/5.
Correct. 5.32
1.5
minus
minus 1.5.
divided by काही नाही येणार, right? Okay. And due to the load acting on span BC. So what is that? Minus, what is the load acting on span BC?
17.
Yes, 17 into the distance is now 2.32, right? 2.32 into 2.32 divided by 2. Okay. संपला का moment?
Ma'am,
BC?
RB
Yes, RB is still remaining. So what is the value due to RB? Tell me. It is plus, right? What is the RB value?
83.44.
दोन्ही पकडलं ना तुम्ही आरबी
येस मॅम.
टोटल शिअर फोर्स पकडला तिथला.
हो मॅम.
टोटल किती येतो कारण परत आता शिअर फोर्स डायग्राम वरती आहे. व्हॉट इज द व्हॅल्यू?
83.44.
83.44 हा into what is the distance? 2.32 right? 2.32. Okay, so this is the moment BC. See, either you can consider left hand side or right hand side, whichever you feel easy, or whichever gives you the less calculation, that you can consider. What is the value?
$16.72.
16.72.
72 kilonewton.
All are getting same value. Verify करा बर का.
16.82 येता है.
16.82.
बरं, ठीक आहे. This is 82. Fine. And now for the last span, MCD. Simply, I will consider right hand side because the calculation is less. So I will get only, what is this distance? It is 2.45, right? So what is the remaining one? 4 minus 2.45. What is this value? Tell me.
0.55.
परत सांग.
1.55.
1.55. So I will simply consider movement reaction at D into that distance and the load, whatever is acting over there. Okay. So what is the expression for MCD? Tell me quickly.
Minus 39.34 into 1.55 plus 25 into
Thumb.
1.55.
Wait. Let me write down. Minus 39 point.
34 into
Uh,
1.55
uh,
plus 25 into 1.55 into 1.55 by 2.
मॅम RD ची व्हॅल्यू 38.89 घेतली आहे ना.
थांबा जरा बघूया इथं काय लिहिलंय. 38.89. So it should be 38.89. $38.89 now. Take this value. Okay. So tell me now, this is divided by 2.
30.25.
30.25. करेक्ट येतात ना व्हॅल्यूज? बाकीचे चेक करा बरं का. Okay, so these are the span moments which we have to consider for design purpose. Okay, this is the span moment for AB, this is the span moment for BC, and the last one is for CD. Okay, and support moments we have already calculated. I will write down once again. Support moments. Tell me the value of moment at support B. It is 28 something. What is the value?
28.74.
And moment at C is 44.44, right? Okay. Now, find out the ultimate shear force. Ultimate shear force means the value, the one which is maximum in all these values. So I'll quickly go to the SFD, which is the maximum value over here. It is this one, this value 61.11. So that is my maximum shear force or ultimate shear force which I have to consider for the design. So I'll simply write down here ultimate shear force is equal to, let us write down it as, denoted as VU, 61.11 kilonewton. For this value now, our shear design will be there. Okay?
मॅम
Yes.
अल्टिमेट SF साठी RC1 आणि RC2 ऍड नसतात करायचे?
नाही 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 नाही, कारण ते दोन्ही पॉझिटिव्ह आणि निगेटिव्ह साईडचे आहेत ना, तर त्या दोघांचं कंबाईंड इफेक्ट हा तो त्या सपोर्टला येतो फाईन, पण बट देर इज अ एक्सटर्नल लोडिंग ऑल्सो, म्हणजे त्या सगळ्याचा विचार करूनच आपण SFD डायग्राम काढलेली आहे, राईट. So the one which is maximum either on the positive side or on the negative side, that we have to consider for the design. Okay.
ओके मॅम.
All right. Now I want to show you one slide over here. When we design the continuous beam for the moment, whatever I have written is we needed to consider. Now what I have written, I will simply read it. A continuous beam is subjected to sagging bending moment near the midspan and hogging bending moment near the support. Okay. So I will again go back to this right up here and I will simply draw a diagram. I will simply draw a diagram here. So this is my A point. This is my B point. This is my C and D. We have already calculated the span moment and the support moment. So how these moments are there? So within the span, the moment is like this, or because of that moment, there is a sagging in span AB. Then at the support, there is a hogging moment. Again, at the span BC, there is a sagging moment. Again, support hogging moment, and then it is 0. Okay, so this is negative, this is positive, this is negative, this is positive. Okay, so in the midspan, there is a, what is the moment here? It is sagging bending moment. Okay, your beam is getting sag. So a continuous beam is supported, a continuous beam is subjected to sagging bending moment near the midspan and hogging bending moment near the support. So for sagging bending moment, compression is at the top, whereas for hogging moment, compression is at the bottom. So again, I will go to this diagram. So this is my sagging moment, and for sagging moment, how my beam is bending, it is bending like this. So if I will consider a cross section of a beam, the portion below the neutral axis is in tension and portion above the neutral axis is in compression for this particular bending action. Okay, now if I will go to the support B, the bending is like this. Okay, the beam is bending in exactly opposite direction. So due to this bending action, what will happen? The portion above the neutral axis is in tension and portion below the neutral axis is in compression. Are you getting this point? At support B, the beam will bend like this. It is exactly opposite to this. The beam will bend like this. So when we consider a cross section of a beam at support B, the portion above the neutral axis is in tension and portion below the neutral axis is in compression. Okay, so just keep this concept in your mind and read the statement again. Okay, so for sagging moment, compression is at the top, whereas for hogging moment, compression is at the bottom. Now, as per our assumption made in limit state of collapse of lecture, what is that assumption? Ignoring the tensile strength of concrete. So, whenever there is a tension zone in the beam, the concrete present in that tension zone, its tensile strength is ignored. That is our assumption made by limit state. So we are not considering the concrete in the tension zone at all. Okay, we are considering only the steel. If you remember all the formulas which are used for finding the MUR, that is ultimate moment resisting capacity of any beam. MUR formula we consider only when we apply it for the tension zone. When we consider the force in the tension T into Z, we consider only area of steel. We are not considering area of concrete there, area of beam there, because of this particular assumption that we have to ignore the tensile strength of the concrete. Okay, so if we'll consider again what is happening with continuous beam for sagging bending moment, that is the portion in the span of the beam, the portion of the slab is in on the compression side. The portion of the slab is on the compression side of the beam, and hence it is considered as a part of beam and it is designed as a flanged beam. Okay, so if I will go back to this diagram here, in this portion, in the mid span, the neutral axis is, or the portion above the neutral axis is in compression, and that portion we have to consider while calculating MUR or while designing the beam. Now in this case, the slab present in the span AB is on the compression side. So that slab will take participation in resisting the moment of resistance shown by the entire beam. So for this entire span, we will consider the presence of a slab in the beam, and hence we have to design a beam like a L beam. L beam because our beam is a L beam in this particular problem. But what is happening at the support? I will go back to the slides. At the support, where this hogging moment is there, slab is on the tension side. Okay, so if we'll consider this diagram again, the slab is in tension side and we have to ignore the tension shown by the concrete, tensile strength shown by the concrete. So slab portion near the support is completely ignored, and we have to design the beam as a rectangular section. Okay, so the same is written here. If I will complete the statement what we were reading. Whereas for hogging moment, slab is on tension side, hence concrete is to be ignored, therefore designed as a rectangular beam. So at the support, we have to design the same beam as a rectangular support, and at the span, we have to design it like a L beam. Okay, and we have already learned how to design a beam as a rectangular section and as a flanged beam. The concepts are different for finding the MUR. The formulas are little different. Okay, so wherever we have calculated the span moment, those are considered for designing the L beam, and the support moments, obviously there is no support moment at A and D, or it is 0. So whatever the support moment is there at A and B, for that we will design a beam as a rectangular beam. Is it clear to everybody? Because this is very important to understand why we have to design it, and this will require for completion of your term work as well. Okay, is it clear to everybody? Students?
Yes, ma'am.
Okay, so let us consider first the flanged section. Let us consider further here. The next step is finding the moment capacity in the design, moment capacity. So here to find out the moment capacity, we will consider first the flanged section. दिसते ना word file तुम्हाला?
Yes, ma'am.
Flanged section. Okay, now when we design the flanged section, we always consider first one assumption, that we assume that the neutral axis is lies in the flange. Okay, there are three cases in the design of flange section: neutral axis lying in the flange, neutral axis lying in the web, and in second case again there are two cases. the 3/7 XU is less than DF or it is greater than DF, or XU is less than 7/3 DF or greater than 7/3 DF. So to avoid the complicated calculations, when we go consider second case, we always assume that our neutral axis lies in first case, that is the neutral axis lies in the flange. Okay, so just write down that statement. Assuming neutral axis is in the flange, neutral axis is in the flange with XU equal to, now we don't know what is the depth of neutral axis, so we assume it as the depth of the flange or depth of the slab. So here in our example, the depth of the slab is 120 mm. So we have considered the XU value as 120 mm. So we find out now the ultimate moment of resistance. Ultimate
मॅम तुम्ही काही लिहिताय का काही
दिसत नाहीये.
मॅम ते आधीच डायग्राम एसएफटीचं तेच.
अरे रे, काय त्रास आहे याचा. ठीक आहे. बघा बरं दिसतंय का आता.
येस मॅम.
Yes, ma'am.
दिसत आहे मॅम.
Okay. So ultimate moment of resistance we will calculate now for the flange section. Here we denote it as mu1 because we have to compare it with the mu value also, and if our mu1 is coming greater than the mu value, that is span moment, whatever we have calculated earlier, then our assumption is correct. If not, then we don't go to the next stage, that is neutral axis lies in web, that we don't consider, we avoid it practically. We increase the dimension of the beam and we repeat the entire design again. Okay, let us hope that this will not come in our case. So what is the formula for finding mu1 now? It is 0.36 FCK into BF into XU into bracket D minus 0.42 XU. Okay, so put all the values now here. 0.36. What is the FCK value? It must be given in the problem statement.
25.
25 or 20?
25.
25.
Pakka na? Because why I feel that it is 20.
No, ma'am,
It
25.
is 25. Okay. So this is 25. Then what is the BF value?
765.
765 into XU we have assumed as 120. So this is 120. What is D value? Effective depth?
450.
450 minus 0.42 into 120. So find out mu1.
330.149.
330.149. So let us consider 15. This is in kilonewton meter.
Yes, ma'am.
Okay. Now compare this value with the span moments. We got three different values for span moments. Out of the three, we are designing now. Actually, we consider the same design for all three spans. Whether it is span AB, BC or CD, we do not consider their design separately. Design means we do not calculate the area of the steel separately for all these spans. Okay. So, moments we do not calculate separately. Area of steel, yes, we need to calculate separately for all the three spans. So what is the moment value? Or for your better understanding, compare this mu1 value for MAB with MAB, MBC and MCD. What is the MAB value? Span moment?
13.5.
13.5. So mu1 is coming greater than MAB. So I will simply write down this greater than MAB. What is the span moment for BC?
16.82.
Yeah, so this is again greater. So it is greater than MBC. And what is for CD?
30.25.
Yes, so it is greater than MCD also. So our assumption is correct. That is the neutral axis lies in flange. Okay, neutral axis lies in flange. Now, if you consider the mu1 value and MAB value, there is a huge difference, right? mu1 is 330 and MAB is just 13, right? 13, 14, some value. Okay, MAB, MBC and MCD. I will go back to these values. MAB is 13.5, MBC is 16, MCD is 30. So if you consider this moment and for this single moment value, mu1 value, if you design, your design will become heavy. Heavy means your design will become uneconomical because unnecessarily we are providing the additional steel, which is not actually required. Okay, so when we calculate the percentage of steel required or area of steel required, we consider the MAB, MBC, MCD value and then we calculate it separately. Okay, so the next step is calculation of main steel. This we are doing for the uh, flange section. Now where we consider the flange section, I will simply write down here in the bracket that this we are considering near the midspan. Near midspan. Okay, so let us find out the area of the steel or calculation of main steel. I'm going to extend the lecture by half an hour because I want to finish this problem today. Calculation of main steel. Okay, so AST, what is the AST formula now for the flange section? It is the same one, the same formula which we use for the rectangular section, that is 0.5 FCK upon Fy into bracket 1 minus under root 1 minus 4.6. Now here we are doing the calculation for span AB. So I will write down here at span AB. This is for span AB only. So 0.46 MU MAB I will write down here because whatever is the span moment for span AB that we have to consider, divided by FCK into BD square bracket complete BD. Okay, now here we are designing this as a flanged section. So B will be BF everywhere. Okay, now put all the values in this equation and find out AST. So this is 0.5 into 25 divided by FC. What is Fy value? I think 415, right?
415.
Yes, ma'am. 415.
415 into bracket 1 minus root 1 minus 4.6. What is the MAB value?
13.5.
13.5. Convert it into Newton mm. So multiply by 10 raised to 6 divided by FCK is 25. What is the BF value?
765.
765 into D is 450. 450 square bracket complete. I will write down here. BF is 765 again into 450. Okay, so find out AST. So this is the AST for span AB. AST AB I will write down here. Do the calculation and tell me the value.
$83.46.
83.46 mm square. It is very small, huh? If you compare the earlier problems, whatever we have solved for singly, doubly reinforced or flange section, the area was more than 200 or 300 mm square. This is very small, 83.46. Compare this with AST minimum and maximum value. AST minimum. All of you just do the calculation for AST minimum, AST max. And we need to wait for 2 minutes because I got one urgent call. So hello? Students, are you there in the class?
Yes, ma'am.
Yes, ma'am.
Yeah.
Yes,
Please
ma'am.
tell me AST minimum value. AST minimum formula
705.09.
0.85 BWD upon FY. This formula you have used.
Yes, ma'am.
So tell me the value. 7. Students. What is the value?
211.98.
211.98. Okay. And AST max is to be calculated for 0.04 BD, right? So what is this value you're getting?
4,600.
4,600. Okay. Now your AST AB value is coming very, very less as compared to the minimum AST. So we have to provide the minimum AST. So provide AST is equal to 211.98 mm square. Okay, minimum whatever is the area of the steel required, that we have to provide compulsory if our AST value is coming less than AST minimum. Okay, this is not actually getting satisfied. So find out the number of bars. Now the area required is very small, so I will assume 12 mm diameter bar. So assuming or using 12 mm diameter bars, number of bars, let us calculate.
1.87.
1.87, so it is 2 bars. Okay, so just write down one statement here, providing two numbers 12 mm diameter bars adds tension reinforcement near midspan of AB. Near midspan of AB. Tension side means bottom, at the bottom of AB. Okay. Now similarly, now we have to do the calculations for next span, that is span BC. Okay. Use the same formula of AST and put all the values. Now instead of MAB, you have to consider MBC. So I will simply write down here the equation and or the formula you write down, or you put all the values and tell me the value directly, because we have already
मैम आवाज
completed.
ब्रेक होते तुम.
I'm going to write down the equation only here. Okay, so it is 0.5 FCK upon Fy into bracket 1 minus root 1 minus 4.6. Here now the moment of span BC you need to consider. FCK BFD square into BFD. Okay. Put all the values in this equation and tell me what is AST you are getting for span BC. Minimum and maximum value we have already calculated for AST. Those values will remain as it is. So tell me what is AST BC you are getting.
104.1 ml square.
So this value is again not greater than AST minimum. Okay. So AST minimum is something 2, what is that value? 211. So it is still less than 211. So we have to provide minimum AST. So provide AST is equal to AST minimum. So as per the span AB, for span BC also, we have to provide the two numbers of 12 mm. The calculation will remain same, na? This calculation will remain same. So I will simply copy this and write down the same sentence there. All of you also are requested to write down the same sentence over there. I hope it will get copied. Yes, so write down this sentence again. Provide two numbers 12 mm diameter bars as tension reinforcement near midspan of BC. So I will make correction over here. Near midspan of BC. Okay, now the next calculation, that is for span CD. Again, same formula of AST you have to use, only instead of MBC put the value of MCD there and tell me what is AST you are getting. I will simply write down AST CD.
One 180.69 mm square.
186.
No, 180.69.
180.7, right? 69 means 7. So this is again not coming greater than AST minimum, or in other words it is less than AST minimum. So I have to provide AST again for CD as AST minimum. So provide AST CD is equal to AST minimum. So again you need to provide two numbers, 12 mm diameter bars at the bottom of span CD. Okay, so we have completed the design for the span movements. That is, we have designed the flanged section now. Now let us come to the rectangular section, which is near your support. Okay, so I will come to the next point, that is rectangular section. For rectangular section, we have to check first what is the moment capacity when we use the beam as a rectangular section. So this is over the support. This is over the support. So for rectangular section, we calculate the MUR max. It is 0.36 FCKB into XU max into bracket D minus 0.42 XU max. So find out the value of XU max for FE415, put the value here and tell me what is the MUR max value you are getting. B, you have to consider as a BW value because we are considering it as a rectangular section. So this is simply 300. Don't consider BF there, it is BW. Or simply B, because for rectangular section there is no question of writing B as BF or BW, it is simply B. So what is the MUR max value you are getting? Students, are you doing the calculation? Hello?
Ma'am, B 230.
230 300 काय आपण अज्युम केलं होतं सुरुवातीला?
230 width of support.
230 घ्या, 230 राईट.
Mm, 99.26 kilonewton.
99.26 kilonewton
kilonewton.
meter. Yes. Compare this with the support moment values. So what is the support moment at B? MB value? It is 28 point something, right?
28.74.
And at C it is 44.44. So these values are greater than the support moments. So we have to design this as singly reinforced beam. Design as singly reinforced beam. If not, then you need to go for a doubly reinforced beam. Okay, so this is very important. Singly reinforced beam. See, in your term work, if you don't want to move to doubly reinforced beam, then you need to change the value of B or D. Change the value of B or D. Once you change over here, the same change you need to apply for the flange section also. So you can consider that these calculation of moment capacity together first. That is, first we'll calculate for flange section, then rectangular section, and then directly we'll go to the calculation of main steel for flange and rectangular. In this fashion also you can do, or you can do in this way also. Okay, so design as singly reinforced section. So for singly reinforced section, again we have to calculate the area of steel. So for calculation of area of the steel, again we have to make use of the same formula. AST is equal to same formula. So I will just write down here rectangular section. That is over support B. Again there are two supports, right? So over support B, I have to calculate AST.
Ma'am?
Huh?
Nothing.
0.5 FCK upon Fy into bracket 1 minus root 1 minus 4.6. Now we want to calculate over support B, so I will write down here MB. Whatever is the moment at support B, that you have to consider for calculation, divided by FCK into BD square. B will be 230 here, into B into D. Okay, put all the values and tell me AST. What is the value you are getting? Tell me AST.
One 182.31.
182.31. Okay. Now compare this with minimum and maximum. The minimum and maximum AST value will not change. So this is still not coming greater than AST minimum. Okay. So again, here we have to provide minimum reinforcement at the support. So provide AST minimum equal to, what was the value of AST minimum? It is 211, right?
Yes.
Mm square over support B. So again, if you calculate the number of bars for this, you'll get the same. So it will be 2 bars, 2 number of bars of 12 diameter. This will remain same. Okay, for support B. Now this reinforcement you are going to provide as a tension reinforcement, and for support the moment is a hogging moment. So tension will be on the top. So this provide, simply write down the statement again, provide 2 number of 12 bars, 2 number of bars of 12 diameter as tension reinforcement near support B, at the top. At the top. Okay. Now similarly for support C, you need to do the calculation over support C. Again, there will be a rectangular section. So over support C, again calculate AST. I am not going to write down the formula also now. You must have learned that formula now. It is 0.5 CK upon Fy into bracket 1 minus root 1 minus 4.6. Here you need to put the moment at the support C, MC, divided by FCK BD square out of the bracket B into D. Put all the values and tell me AST at the support C. So this I will write down as ASTC.
Two 286.86.
286.86 mm square. Now this value is coming greater than your AST minimum. So we have to provide this area now. Okay. So for this we need to find out again the number of bars. So number of bars will be 286.86 divided by, I will consider 12 mm bar only. So pi d square by 4. I will consider 12 mm bar. So you can simply write down one statement about this, that assuming 12 mm diameter. Tell me number of bars.
2.54.
Yeah, 2.54. So it is 3. Okay, 3 bars. So just write down a statement. Provide 3 12 mm diameter bars adds tension reinforcement over support C at top. Okay. And the next step is design for shear, which you are going to do as homework. Okay. Design for shear. Do this as a homework. Now I will show you quickly how the diagram will appear for this continuous beam. So this is a sample diagram which I have included here. Okay, so you can see here at support B, a section is taken, sorry, at support B, this is A. At support B, a section of BB is taken, and at section BB, the details of reinforcement are shown. So 2 bars of 12 mm diameter at the bottom, and these are the minimum bars which are provided at the top. Sorry, this is the minimum, because at the support we calculated 2. Here at section BB, actually we have provided minimum AST, so it must be 2 of 12 mm bar diameter. Okay. At support C, here you can see at support C a section DD is taken, and there will be 3. This diagram has been little bit changed. Okay. And for the mid span AB, again here you can see it is a L beam. At the bottom, this is our design reinforcement to 12 mm diameter, and this is minimum 212 at the top. Okay, and whatever the shear design you will find out accordingly, the details you have to go write down here. Okay, so when you draw the diagram for continuous beam ABCD, this is the longitudinal section of the beam. All the details you have to show, the details of stirrups will be mainly observed in this longitudinal diagram. And at every point for midspan AB, you have to take one section and draw its cross section. Over the support B, take a section, draw its cross section. For BC, take a section CC at the midspan and draw this cross section. Okay. So for midspan, there is L beam, and at the support, there is a rectangular beam. This is wrong. At D, there is no movement. So this diagram is not expected. Okay. So this is what is the expected diagram. In the same fashion, you have to draw the diagram for your term work also. Okay. Now, one little mistake we have done in the calculation, I want to rectify that. When you go to the load calculation here, this formula there was a typo mistake in this formula. If you recall the formula, earlier I had given it as WL WS into LX by 4 into bracket 1 minus 1 upon beta. So the formula is like this. WS LX by 2 into bracket 1 minus 1 upon 2 beta. And because of this change, obviously your value of the load acting on longer beam will change, and further calculations will also change. But values will change. Your design philosophy, the design steps will remain as it is. Okay. So for this corrected value or rectified value, you can do the calculation and solve the same problem as a homework, as a practice problem. Okay guys, is it clear? So we have completed design of continuous beam. We will stop here and I will give you this attendance link in your chat box. Have you got the attendance link now in your chat box?
Yes, ma'am.
Give the attendance through the link only or link also. Just check whether that link works or not. Otherwise, I will give the another link.